Hello all, welcome to my channel Simple Concepts by DJ. Today we are going to see a very important chapter, that is application of differential calculus, okay, which is very important for NCERT syllabus of class 12. Okay, so the most important thing here about the application of integral calculus is the area, the area bounded by simple curves. This is the topic today, area bounded by simple curves. Okay, simple curves. So if I draw a curve like this, and if you are asked to find the area that is being enclosed by this curve, it would be very difficult for us to find the area that has been enclosed by this curve. For example, if this is a square, everyone knows that this is a square, right? So what will be the area of the square of side A? If the side is A, means the area of the square will be A squared. We can calculate the area of this square. Similarly, for a rectangle, if it is going to be for a rectangle, this is L, this is B. So length into breadth. So with length and the given breadth, we can find the area as L into B. And for similar shapes, like if it is going to be for a trapezium, if it is going to be for a trapezium like this, trapezium will be like this, in this form. So if I want to find the area of the trapezium is nothing but A is equal to half into A plus B into H, where A and B are the base, two sides, and height is this is the height. Okay, so with height and the two bases, I can find the area of the trapezium. So these are all definite shapes. Okay, a square, this is a square, right? A square is a definite shape. A rectangle is a definite shape. A trapezium is a definite shape. With the help of this definite shape, you can find the area. So that is not a big issue. But in the case of a curve, a simple curve like this, if they give these, let the equation of this curve be y is equal to f of x, and if they are asking to find the area of this curve y is equal to f of x, it would be very easy. Area bounded by the curve y is equal to f of x means it will be very complicated for us to calculate the area. So what is the simple thing that we need to do it is, first thing is that we need to take a small portion that is called as an elementary area. We need to consider an elementary area, and we need to find the area of that elementary area. Then once we find the area value of that elementary area, we can simultaneously increase the area. We can add these elementary areas and we can get the total area of that total area that is being bounded by this curve y is equal to f of x. Okay, so let's get into the concept in detail, right? So for example, like I'll be given a curve like this, y is equal to f of x. Let the curve be, equation of the curve be y equal to f of x, right? So this curve is drawn in a graph. So this is the graph. Okay, so this is x-axis, this is y-axis, and this is the origin. So what is the area that is being bounded by this curve? The total area that is being bounded by the curve y equal to f of x. In order to find the total area bounded by the curve y equal to f of x, the first step what I am supposed to do is, I am going to take a point here. Let us assume that this point is S. And I'm going to mark another point here on the curve, let it be R. Okay. So now what I'm going to do is, I'm going to draw a perpendicular line from S such that it meets the x-axis at a point P. Okay, it meets at a point P. So this line is called as an ordinate. SP is an ordinate. Okay, so let the equation of this ordinate be x equal to A. X equal to A. Similarly, I'm going to draw another perpendicular line from R, starting from R, and it meets the x-axis at the point Q. So now the equation of the ordinate RQ will be x equal to B. Is x equal to B. Okay. So now what I'm going to do is, I'm asked to find the area, this entire area I am supposed to find. So it is very difficult, it is very complicated for me to find the entire area that is being bound, but that is being enclosed by this curve. So what I'm going to do is, instead of finding the entire area, because here the portion is regular, but here it is not regular because the function keeps on increasing here. So I won't be able to find, I won't be able to arrive at the correct value of the total area. For that reason, what I'm going to do is, I'm going to consider a small portion, a small elementary area. I'm going to take it and I'm going to find the area for that one. So what I'm going to do is, let us connect. This is the area that is being enclosed. So what is the area? Area is nothing but, see, PQRSP. This is the area. See, PQRSP is the total area. This one is called as the total area that is being enclosed by the curve y is equal to f of x. Right. So now I'm going to consider a small strip, a small vertical strip, such that the length of the vertical strip be small y, and the breadth of this vertical strip, be dx. Why I'm giving dx means, because the axis is x-axis and this vertical strip is occupying a small amount of path on the x-axis, so I am giving it as dx. Dx is a small path that has been occupied by this vertical strip on the major x-axis, right? So it will be like this. Okay, if I zoom the vertical strip, it will be like this. So this is y, this is the length of the vertical strip, that is y, and this part is nothing but, the breadth is nothing but, this is called as dx. I am naming it as this portion as dx. So what will be my area of this vertical strip? My area of the vertical strip will be y into dx. Y into dx will be my area for the vertical strip. Similarly, here also I'm erasing it. Here again, this is the vertical strip, right? I'm shading it in order to identify for the purpose of identification. I am shading it. Okay, so this is the vertical strip. The length of the vertical strip is y and the breadth is dx. Okay, so the area means dA. I'm denoting it with dA. dA is nothing but, it is called as the elementary area. So dA, elementary area, is nothing but this y into dx. So this is the value of this vertical strip. The area of the vertical strip will be dA, which is nothing but y into dx, right? So now what I'm going to do is, so let us keep it as it is. So now I'm interested to find the total area. So total area, how can I get the total area? So see, this is the vertical strip. This vertical strip has a tendency, I can to move from here to this point, from this point to this point. In order to find the total area, I need to move this vertical strip from the point P to the point Q, such that my limit will extend from x equal to A to x equal to B. Okay, so this is the thing. So in order to find the total area, what is the total area? Total area, see, total area is nothing but, capital total area will be area, that is nothing but PQRSP, that is PQRSP. This is my total area. This total area, I am denoting it with capital A. Capital A is nothing but, it is nothing but integral of small, this one, small, this vertical strip, area of the vertical strip. Area of the vertical strip is nothing but dA, right? dA, and I'm going to fix the limits, because dA, if I take this dA, it is only for this vertical strip, but I am interested to find the total area. In order to find the total area, what I'm supposed to do is, I need to integrate dA by fixing the limits. My limits ranges from x equal to A to x equal to B. That is, x equal to A, x equal to B is nothing but the ordinate. Okay, so it extends from A to B dA. So if I do this, I'll be getting this area. So again, which is nothing but, integral tends from A to B What is dA? We have found it earlier. dA is nothing but the area of the vertical strip, which is nothing but the length into breadth, that is y into dx. Okay, so the integral a to b, dA is nothing but y into dx. This is y into dx. So now again what I can do is, which is nothing but integral tends from a to b, y is nothing but f of x. Okay, so f of x into dx. Therefore, this is the area value. So the area value is integral tends from a to b f of x into dx. So if you integrate the function, if you integrate this function by setting up the limits, you will be able to find the entire area value, the total area value that has been enclosed by this curve, which is having an equation y equal to f of x. Okay, this is case number 1. This is case number 1. Okay, so now we are going to discuss about case number 2. So what is case number 2 is, see, this is, I'm going to explain the case number 2. Here now we are going to discuss about another thing, that is case 2. Case 2. So here again I'm going to consider a graph that is capital X O Y. As we discussed in the previous case, what is happening is, in a previous case, that is case 1, we were considering about a curve like this, and we named the equation of the curve as y equal to f of x. But now what are we supposed to do is, we are going to consider a curve which is of this form. If the curve is like this, if the curve is like this, so how we need to find the area that has been enclosed by this curve? We need to find, we are interested to find the area that has been enclosed by this curve. So what we are supposed to do is, we need to find the equation. We need to name the equation of this curve. So the equation of the curve be, instead of y is equal to f of x, the curve equation will be x equal to g of y. X equal to g of y. And now again, similar like how I did case 1, the same procedure should be followed in case 2. Only thing is that the curve will be, the direction, the orientation of the curve will be different, and the equation of the curve will simultaneously will be different from the latter. I mean, by the previous curve. So for this, I'm going to take a small point. I'm going to take a point over here on the curve x equal to g of y, and I'm going to draw a perpendicular. Let it be P. Okay, let this point be P. From P, I'm going to draw a vertical line. And it meets the y-axis at a point Q. Let us assume it meets the y-axis at a point Q. Similarly, I'm going to take another point on the curve, and I'm marking it as R. From R, I'm going to draw a perpendicular line such that it meets the y-axis. PQR, let it meet the y-axis at S. Okay, so this is what the curve. So we are interested to find the area of the curve. So we are interested to find the area of the curve. Area of the curve is nothing but PRSQP. So PRSQP. So this is the area of the curve which we are interested to find. But directly we cannot find the area of the curve because it is very difficult, because here, even though this orientation, these lines are regular, but here the curve is not regular. Okay, it is increasing. So at each and every point on the curve, there is an increase in value. So we won't be able to find the exact value for this curve. So what are we supposed to do? Similarly, the one which we did, we need to consider a vertical strip. Okay, this is a vertical strip. We need to consider it. Okay, so this is a vertical strip. I am shading this vertical strip for better identification. Okay, I am shading this for better identification. So this is a rectangular strip, a horizontal strip. This is a horizontal strip. Let the length of the strip be x. I am marking the length of the strip to be x, and the breadth of the strip the breadth of the strip is dy. Okay, a small amendment is what I'm doing here. The length of the strip, length of the horizontal strip is x, and the breadth of the horizontal strip is dy, right? Simple. Now, if you want to find the area of this elemental strip, the small horizontal strip means area is simple. So, dA, which is nothing but x into dy, x into dy. This is the area of this horizontal elementary strip. So now we are going to fix the ordinate. So Rs is an ordinate. So I am giving this ordinate as s equal to, or just like x equal to, or y equal to, small y equal to c, and this be, let it be y equal to d. Okay, so this equation of the ordinate be y equal to c, and this one be y equal to d. So that is, what I'm going to do is, in order to find the area of the total area, if I want to find the total area, what I'm going to do is, I'm going to move this horizontal strip from RS to QP. I keep on moving. Once I find the area of this elementary horizontal strip, from here onwards, I keep on moving in order to find the total area that is being enclosed by this curve, having an equation x equal to g of y. So what I'm going to do is, this is what I'm going to do. So now I can find the area that is being enclosed, the total area that is being enclosed by the elemental curve. So for that, let the total area be capital A, which is nothing but integral tends from C to D. That is from C to D. And what is the equation? Equation is, dA. dA is nothing but the area of this horizontal elementary strip, dA. So which is nothing but integral tends from C to D. dA is nothing but x into dy. So I'm substituting x into dy for dA, x into dy. So again, which is nothing but integral tends from C to D. X is nothing but x equal to g of y, which is the equation of the curve. So I'm substituting the value of the curve equation in this. So x into dy is nothing but g of y into dy. So therefore, this is the equation. This is the area of the curve. This is the formula to find the area of this curve. Area of the portion that is being enclosed by this curve. Okay, which is nothing but integral tends from c to d g of y into dy. Okay, this is how I can find the total area, right? So this is case number 2. This is case number 2. So we will be discussing about case 3, right? Now we'll be discussing about case 3. Okay, so now we'll be discussing about this same curve, but it will be in a different orientation in a different axis. So I'm naming it as case number 3. Case number 3, let this be the axis. Okay, this is y axis, this is x axis, and this one is y dash. This is origin, right? So my curve will be like this. If my curve is like this, the curve equation is similar. Y is equal to f of x. Now, if I want to find the area that is being enclosed by this curve, again, similarly, I am going to mark 2 points over here. I am putting it as P, this one as Q. I am extending the line such that this line meets the x-axis. Similarly, I am going to draw a perpendicular line such that this perpendicular line meets the x-axis here. The point where this perpendicular line meets the x-axis be R, and the point where the Q, this perpendicular line meets the x-axis be S. So now PR is an ordinate. Similarly, QS is also an ordinate, right? So both are ordinates. So this ordinate QSB x equal to a be defined by the equation x equal to a, and this ordinate PR be defined by the equation x equal to b. Okay, so now you are interested to find the area of this area. Okay, the value of the area enclosed by this curve having an equation y equal to f of x, right? So now it is very complicated to find the entire area. So now what I'm going to do is I'm going to apply this small strip. I'm going to consider a small strip, a vertical strip. Okay, I'm going to consider a vertical strip. The vertical strip will be like this. So the length of the vertical strip, will be minus y, because this axis have negative values. This y axis value will have negative values. So this portion also will take negative value. So the length of this vertical strip will be minus y, but the breadth will be same, that is dx. So now what will be the area of this elementary and this vertical strip, which is nothing but minus y. It will be minus y into dx. This is the area of this. Minus y into dx is the area of this elementary this vertical strip. So what we call it as the elementary area. This is called as the elementary area. So this is, so what I'm going to do is dA is nothing but minus y into dx. dA is nothing but minus y into dx. So this is the elementary area. So now what I'm going to do, this is the area which I am interested. I'm going to find the value of this entire area. So I'm going to do as A. Let A be the area. A equal to integral tends from, so we have the limits from A to B. So it limit tends from A to B. So what is dA? dA is nothing but the elementary area. So now again, what I'm going to do is, which is equal to integral tends from A to B. dA is nothing but minus y into dx. Before previous term and all, in case 1 and all, we were looking only for, we were having this positive value of y into dx. We had this dA is equal to y into dx, positive value. But here, this dA is taking a negative value because it falls in the XOY dash axis. So XOY dash plane. So the value itself will take a negative value. So what I'm going to do is integral tends from A to B, and this dA value I'm substituting it as minus y into dx. Minus y into dx, right? So what is minus y into dx? Y we know that is the equation of the curve y is equal to f of x. So I'm going to substitute over here, which is integral tends from A to B minus y is nothing but f of x into dx. F of x into dx. This is the total area. Total area is integral tends from minus f of x into dx. So, but what happens is area doesn't have negative values. Areas usually have positive values, but we have negative values in our equation. So, what we are supposed to do? We need to remove this negative value. So, how you can remove this negative value? The only way, the only solution what we are supposed to do is we need to consider the absolute value. So, for taking the absolute value, we need to put modulus. So this again I'm going to write it as A will be integral tends from A to B. So I am removing this minus f of x into dx. For removing this negative sign, I am going to apply a modulus. This is absolute value. So A is equal to modulus integral tends from A to B f of x into dx. So this is the area formula to find the area enclosed by this curve, which lies in the XOY dash plane. So this is the formula. Okay, this is case number 3. And case number 4, you have another, if you can have, you have another similar condition. That is case number 4 is case number 4. In case number 4, what will happen means you have this axis like this. You'll be having an axis like this. Sometimes the curve will be oriented like this, in this direction. In this fashion, the curve will be oriented. So if the curve is oriented like this, what will happen is, here, this is the ordinate. So let us assume that this is the ordinate. The equation of the ordinate is x equal to a. And similarly, this is the ordinate, the final ordinate. So let us assume the equation of this final ordinate to be x equal to b. So x equal to b. So the strip is here. You need to consider this vertical strip. Similarly, here also you need to consider the vertical strip for finding the elementary area. So you need to find the elementary area. So in this case, what will happen? Your area itself will get a negative value because it falls in the x, o, y dash plane. So this is because y dash has a negative value. So it falls in this plane. So automatically your area, let a1 be the area. This area will take a negative value, minus a1. Similarly, in this one, if you take this portion of the curve, here the area will be a2, but it will be a positive area because it lies in the XOY plane. XOY plane. So it is all a positive. Positive values. X takes positive value, Y takes positive value. So it lies in the positive region. So the area which is being obtained over this will be positive and area will be negative. So what will be the total area of this continuous graph, of this continuous curve? A. If A be the total area of this curve, A is nothing but A will be A1, this minus A1 plus this A2. So this is the total area. But in our case, we cannot take area to be in negative. Area doesn't have any negative values. So we need to take positive value. For taking positive value, what we are supposed to do is we need to take modulus. Modulus of A1. If I take modulus, the negative value will be automatically converted into a positive value. So I'll get positive value. So my area 1. So the area value at this region will turn out from a negative value to a positive value because I have taken a modulus over here. So minus A1 will be plus A1 and I take modulus. Modulus of A1 plus A2. Okay, this is the total area. So this is the final case. Okay, so in order to find the entire area, I need to take modulus such that I can remove this negative sign. So A1, negative A1 will be converted into positive A1 plus A2. So A1 plus A2 will be, I'll be getting the total area that is being enclosed by this curve. Okay. Thanks for watching. Please do subscribe my video for more upcoming and latest and more informative sessions. Until then, it's me signing off for now. Thank you.